This one for all my peeps that pass. God bless they rest. And check it out. Now I'm pound cause it's mad real.
Yo, it's time for Carnegie Mellon University's Future Data Systems Seminar Series. This seminar is made possible by Google.
Guys, we're super excited today to have Ian Cook. That was not a Freudian slip, I promise you. He's the co-founder and CEO of Columnar. He is ex-Ursa Labs, which is the original company backing Apache Arrow. Then he's ex-Voltron. And since then, he's taken all his stuff he's learned about Apache Arrow and working with Apache Arrow Flight and everything that's about today. And they have a new company called Columnar. They have money. He'll talk about it later, but not now. And so, Ian, thank you so much for being here. If you have a question for Ian, either post in the chat or better off unmute yourself and just interrupt at any time. And that way, Ian's not talking to himself for an hour on Zoom. Ian, thank you so much for being here. The floor is yours. Go for it.
Thanks, Andy. Really appreciate the invite. And yeah, please feel free to jump in, ask questions, interrupt me as I am going. So I'm going to talk today about ADBC, which is a part of the broader Apache Arrow project. So the agenda for this session, I'll start off with a little introduction. Then we're going to jump back in time in keeping with the theme of this whole series. We're going to go back to 2015, then back to the 90s, and then back to today. Then I'll talk a little bit about ADBC, kind of why it exists, what problem it solves, and how it solves that problem. At the end, we'll travel forward in time to talk about the broader vision of what we hope to solve in the future with ADBC, and then we'll have time for some questions at the end. So a little bit about me. Andy mentioned I am a CEO and co-founder of Columnar, previously at Voltron Data. Before that, I was at Cloudera, also during the Hadoop heyday. I went to school for statistics, dropped out before the PhD. And I'm also an Apache Arrow PMC member. And so I want to talk a little bit about, hold on one second, slide glitch. Okay, so I actually, before I learned SQL and databases, I know this is like a database crowd, but before I learned SQL and databases, I was an R guy. This is what happens if you go to grad school for statistics. And so I knew data frames. And really, I only learned SQL when I got my first job in industry after grad school. But in grad school, I fell in love with R, later with the tidyverse. And this actually had a lot to do with why I ended up working on Arrow. So I want to jump back to 2015 and describe kind of the origins of Arrow, which have a lot to do with the intersection of data frames and SQL. So I joined Cloudera in 2015, and this was like a super interesting time for Cloudera and some of these other companies working on Hadoop, because they had all of this big data infrastructure that all ran in the JVM. So this was engines like Hive, Impala, Kudu, Spark later. And what was happening in the meantime was that Python and R were becoming massively popular for data science, data analytics. But for far too long, the Hadoop companies kind of treated Python and R users as second-class citizens. So in 2015, there was like a lot of, oh, if you can't do it with SQL, you need to learn like Java or Scala. So when I joined Cloudera, one of my jobs was to build a bridge between R and the Hadoop SQL engines at the time, primarily like Hive and Impala. And this, if you're familiar with R, there's a nice data frame library in R called dplyr, which defines kind of a domain-specific language for working with data frames, data frame API. It's in memory by default, but there's a package dbplyr, which takes the dplyr API and compiles it to SQL and runs it in a database. So I wore a bunch of hats at Cloudera, but one of the things I was doing was building an Impala backend for dbplyr. And at Cloudera, I met Wes McKinney, who was also there after they had acquired his startup Datapad. And at Cloudera, Wes was tackling exactly the same problem I was, but with Python instead of R. So Wes, had created Pandas earlier, and Pandas obviously went on to become wildly popular. But Wes famously kind of grew to hate some things about Pandas. He wrote a blog post about this. And in 2015 at Cloudera, he was like rectifying some of the things that he, wished he had done better in Pandas. part of the way he did this was by creating IBIS, which is a SQL runs on your database or your query engine of choice, analogous to what dbplyr does in R. But as it turns out, compiling data frame API code into different dialects of SQL, like IBIS and dbplyr do, only solves part of the problem of bridging, R and Python with SQL engines. The other part of the problem is quickly and efficiently getting results out of the SQL engine and into, a data frame in memory in Python or R. This, in some ways, is a trickier problem. And in 2015, like the only real standardized way of doing this was using something like ODBC or JDBC. So in R, most of what was built at the time in dbplyr was built on an underlying package called DBI in R, which most of the time called ODBC drivers under the hood. Likewise, with IBIS, a lot of the databases that you could connect to exposed Python DB API connectors, which many of them used ODBC under the hood. There was a little bit of work on some newer things like Thrift at the time, but there was like a fundamental problem here. I think West realized very early that there was no shortcut around the inefficiency of these underlying standards, and it required a lot of low-level work and coordination with vendors and other projects to solve this problem. So this was when West got together a group of open source developers, including Jacques Nadeau, who co-founded Dremio around that time, and launched the Arrow project to solve this and some related problems. So Arrow in the early days provided little more than a binary format and a very low-level toolkit that enabled interchange like between modules written in different languages, usually in the same process. But it emerged at this kind of critical moment when a lot of developers at the Hadoop companies and elsewhere were all struggling with this low-level data interoperability problem as Python and R and other languages wanted to access all this tooling that was written in the JVM. So Arrow became a smash hit very quickly, and then over the years got implemented in almost every major language. Today, it's used inside virtually every data stack. The Python library for Arrow alone is on track to be downloaded something like 2.5 billion times this year. But what happened also is that as Arrow became a fixture in low-level data infrastructure, it gradually climbed upward and solved like progressively higher level problems and at higher abstraction levels. So although Arrow is almost 10 years old, it was only fairly recently that it became a fixture in things like data connectivity and query result transfer, as we typically understand them. But what the core design choices made a decade ago by West and the rest of that crew turned out, like by foresight, not by accident, to be great for this use case too. I wrote a blog post with my two Columnar co-founders, Matt and David, early this year about this. I'll hit on some of the points from this blog post in this talk. But if you're interested in like more detailed look at what exactly makes Arrow so good for query result transfer, check out this blog post. But one of the questions that immediately comes up is like, so Arrow is great for transferring query results, but compared to what? So I want to start here by looking at the incumbents. Who are we competing against in this data connectivity space? And to do that, we need to jump back to the early 90s, when the first widely adopted connectivity standards were first created. So in the 1990s, I know Andy has covered this in some of his lectures. Virtually all data systems at the time were row-oriented. The earliest column-oriented databases existed only as research projects in the early 90s. And it was at that time, early 90s, 1992 exactly, that the SQL Access Group, which was this group of database vendors, including Microsoft, Simba, a few others, released the first version of ODBC. So for context, in 1992, this was before version 1 of Python was released. That was in 1994. Java had not been released. That wasn't until 1995. So this was, the world was very, very different back then. But ODBC, we had ODBC. A few years later, some son didn't like having to, do foreign function interface to access the databases through ODBC, which was very based on C and C++. And so they created a JVM-based data connectivity standard, JDBC, which they released 5 years later in 1997 as part of Java 1.1. And then also in the 90s, Python, started to become more popular by the late 90s, and PEP 249 was accepted. That is DB API 2.0. So this is a recognizable name for anyone who uses Python. This is still the dominant Python data access API that we use today. So that's the thing that's notable about these standards from the 90s is far from being like something that's drifted off into history. We still use these things today. And that is all the more striking when you look at how much of the rest of data infrastructure has changed in the ensuing years. So I borrowed one of Andy's slides for this. So, as I said, in the 90s and before, the vast majority of data systems were row-oriented. Specifically, like the term that database researchers use is the n-ary storage model. Each row, each entire n tuple is stored contiguously on disk in memory. That was the way things were for the most part before the 90s. During the 80s, but really it didn't happen in earnest until the 90s, there started to be research in columnar data systems. And the term researchers use for this is DSM, or decomposition stores model. What this means, right, is that you decompose the relation, the table, into its attributes, its columns, and you store the attributes contiguously in memory or on disk. This is what we commonly know today as column-oriented or columnar storage model. Starting in the 2000s and 2010s, columnar model became ubiquitous. But in the 90s, it was like virtually unheard of. But yeah, today, if you look, Andy's got all these logos in here. Virtually every like mainstream analytic database system and many other tools like data frame libraries, visualization tools, BI tools, and much more are all use columnar architecture. One little side note, though, many columnar data systems today are not full columnar in the strictest sense. They're batch columnar. This is what's known to database researchers, right, as PAC, partition attributes across. First, you split a table horizontally into like sets of rows, typically called row groups, record batches, something like that. And then within each of those batches, you use the columnar model, the DSM model. This is the model that Arrow uses. This is also the model that Parquet, DuckDB, many other columnar systems and formats use. So PACS gets you virtually all the benefits of the columnar model while retaining some benefits of row-oriented layouts. Like you can keep the attributes in each individual tuple fairly close, in physical proximity. So one thing to note is that like at either end of its limits, PACS converges to either NSM or DSM depending on your batch size. So like with a batch size of one record, it's the same as row-oriented, the same as NSM. With a batch size of the whole table, it's DSM. But in practice, with columnar storage, like most real-world systems use batch sizes of hundreds of thousands of records or more. And so I think, distinguishing PACS as something other than like full columnar, obviously it's important for database researchers to do that. But I think sharpening this distinction can be like a little bit harmful to lay people. Tends to result in people, being unnecessarily pedantic and saying things like, "Oh, Andy Pavla taught me that Parquet is not a true columnar format." So only in this audience would I not just call Parquet and Arrow and DuckDB columnar. All right, side note over. Andy, anything you want to say about that before I continue?
No, that's accurate. That's fine.
Okay.
Yes.
Cool. All right, so I want to drill more into this layout stuff and show you how this applies to data connectivity specifically. So here I'm going to use in the next couple of slides this logical table, which has 3 columns, 6 rows. The rows are all 1, 2, 3, 4, 5, 6, and the columns are ABC. So logically, we would represent it as a table. If we were using a row-oriented layout, the physical representation might look something like this. This is reductive, simplified, but first we store the schema at the beginning. I've just represented that as the header. And then we store each tuple sequentially, from 1 to 6 in order like that, right? But in a batch columnar layout like Arrow, you would instead group those 6 rows into some number of record batches. In practice, like I said, each record batch has like hundreds of thousands of rows typically. But in this simple example, each record batch has 3 rows. So the way that you serialize in a batch columnar layout is, first the schema again, then the first record batch in this columnar layout with, column A, all the values adjacent, column B, column C, and then the same thing for the second batch. So that's, visualization of serialized table in these two layouts. So the reason I show this is because as the world has adopted columnar formats in many source systems, databases, query engines, file formats, etc., and as the world has adopted columnar architecture in a lot of destination formats, single node databases like DuckDB, BI tools, data transformation tools, we've had ODBC and JDBC and DB API and all of these legacy row-oriented transfer formats sitting in between. And what this means is that every time you want to transfer data from a database like DuckDB through something like ODBC to another columnar format, you have to do this big shuffle, this big transpose. And I visualized this here. First you take the header, then you have to take the individual row values, which you've got to grab from different locations in the columnar layout, and you've got to sequence them all in this row-based layout, which means just a lot of compute cost to be grabbing these values out of different locations, a lot of memory overhead, a lot of CPU overhead. All right, so now we've got, the data in the format that something like ODBC expects it in, but at your destination, you've got to reverse the process in many cases. So you've got to grab the locations of the different columns out of the row-based format and, rehydrate the data in the original format you had it in. This is ridiculous. I mean, why would anybody do this, right? Well, the reason everyone would do this is because it's the dominant protocols for connectivity like ODBC and JDBC and DP API just do it this way. This is the way it's been done for 30 years. And so inertia keeps us doing this. So the fundamental question of ADBC and of the other Arrow technologies for query result transfer is, what if we just replaced that middle step with a columnar transfer format, right? Then what we can do is just simply take the data and stream it exactly without any reordering into the transfer format, and then stream it without any reordering into the destination format, and we're done. And this is just incredibly more efficient, does not have to burn up with CPU cycles, does not have to use memory, allows us to do a bunch of other nifty things and just get our results a lot faster and more efficiently. So notably, something to consider here is that since the 1990s, from then to today, CPU performance has increased about 100x, but network speed has increased by about 10,000x. So one of the reasons why these formats like ODBC were perfectly fine in the 90s was that databases and data sources and data destinations were all row oriented. Another one though was that networks were slow, very slow. And so generally the network was going to bottleneck everything. So if you needed your CPU to be running hot in order to serialize and deserialize data, it still wasn't going to be the bottleneck. The network was going to be the bottleneck. Well, fast forward to today, the network is increasingly in query result transfer. The network is not the bottleneck. It's all the serialization, deserialization that's happening at either end that's the bottleneck, because even with multi-core performance, CPUs are, have not improved in performance as much as networks have. And I mean, what these numbers come from is in the 90s, the typical CPU was about 1 gigaflops, right? And today, the typical like desktop CPU is something like 100 gigaflops. Where and in the 90s, if you remember using a modem, right, like something like 56K was common. Today, like gigabit was common. So that's what the math is there. So I am not, the first one to point out that ODBC and JDBC that it's time to replace these 30-year-old standards. So Tomer Sharon, the founder of Dremio, wrote a nice article back in 2019 pointing out, some of the same things I'm pointing out here, that ODBC and JDBC were incredibly inefficient way to transfer data. And Tomer proposed at the time that Arrow Flight, which is this client server protocol based on Apache Arrow, was the solution to this problem. And I think, Tomer had a good point. If every database vendor would implement a full Arrow client server protocol in their service, we could eliminate the need for all of these serialization, deserialization costs imposed by inefficient client protocols, right? But that's a big if. The, you know, Dremio famously embraced Arrow very early, built their whole platform on Arrow. Dremio has a great Arrow Flight and Arrow Flight SQL client server protocol that you can use today to get data out extremely fast. But not every other player in this space has followed suit. And I think, I don't know if any of you are familiar with this concept that Cory Doctorow and others have pointed out. If you want to create interoperability, sometimes you need to do it in an adversarial way. Sometimes the parties that you're trying to get to interoperate don't want to interoperate. The problem with requiring a client server protocol to speak Arrow is that if there's a vendor or an open source project that's in control of what happens on the server side, you have to convince them to add Arrow on the server side in order to take advantage of that. And that is a hard sell for a lot of vendors and open source projects. And so I think like one of the innovations that we had with Arrow is simply removing the need for the server side to do anything in order to make all kinds of query engines, databases, and cloud services speak Arrow. And that was the key insight with ADBC. So I'll spend the rest of this talking about ADBC. So what it is a multi-language data access API spec and driver standard that gives you data in Arrow columnar format instead of a row-oriented format. And it's really a modern alternative to ODBC and JDBC, specifically for analytic applications. So in addition to using Arrow format, ADBC can zero copy data to achieve low latency and high throughput and to reduce processor load and memory overhead. So here's a diagram, describing what ADBC is. And this calls out two distinct options for ADBC, which kind of mirror what I was talking about before. If you have a data source like Dremio that natively speaks Arrow on the server side, in Dremio's case, it implements a Flight SQL client server protocol, then you can use a Flight SQL driver in ADBC, and you can get true Arrow all the way from end to end, out of the database into the driver using Flight SQL, out of the driver into the ADBC API using ADBC, and then to your client in Arrow format. But if you have a database like Postgres, which does not natively have an Arrow-based server protocol, well, no problem. We can still create an ADBC driver for it, but in that driver, we have to wrap some existing protocol that the database understands. So in this case, in this example for Postgres, we wrap libpq, which is a library that implements the Postgres protocol. We bundle that up into an ADBC driver, and then from the user's perspective, it all works the same way. It's just not going to be as fast because it's not true end-to-end columnar format. So that is there's sort of a slow path and a fast path that are baked into the architecture of ADBC, but all behind the same single client API, which enables, like, if you're going to migrate to ADBC, you don't have to wait for each vendor to go and implement drivers, or to go and implement support for some Arrow protocol in order to do that. So I want to talk about what ADBC is and also what ADBC isn't. So it's a client API specification. unlike Flight SQL, like I said, it is not a. Oh, hold on. Let me talk about what it is before I talk about what it's not. Uh, yeah, so it's a client API specification. It's cross-platform. So ADBC works on Windows, Linux, Mac OS. It's cross-language. It uses under the hood. It's a C API, but you could be you can implement it in any language. It's vendor neutral, so there's no the Arrow project is an Apache Software Foundation project, not controlled by any vendor. It's controlled by the Apache Arrow PMC. ADBC is Arrow native. It uses the Arrow Columnar format to transfer query results, and it's an open standard, and all the software around it is open source. So I'll talk about what ADBC is not. Right, it's not a backend. So you can wrap a backend with an ADBC driver, but ADBC itself does not sit on the backend. It's not a wire protocol or a client server protocol. It does not impose any requirements on the server side. All that's needed for a database, a query engine, data platform to work with ADBC is a client-side driver that adapts its protocol, its API to the ADBC API. So it's a client API specification, doesn't define what goes on between your client and the database. Yeah. So another thing it's not is a SQL transpiler. If you want to say, translate some like general API into ADBC, into queries that you send to ADBC to different database drivers, you're also going to need to use something like SQL glot to transpile the SQL queries themselves. ADBC will not take care of that for you. It will dispatch the queries to different databases, all with a very unified API, but it's not going to take care of the problem of converting between SQL dialects. Another thing that ADBC is not, it's not intending to compete with ODBC and JDBC for transactional applications. ADBC is very much about analytic queries, OLAP applications, not OLTP. Honestly, things like ODBC and JDBC are really fine in most cases for ODBC. Sorry, for transactional applications. So we're not trying to compete there. Dupiaman, did you have a question?
Yeah, since you said can I interrupt you. When you mentioned that it's not a SQL transpiler, and you said you'd have to use something like SQL glot instead. So when Substrate, for example, goes to ADBC, does that still mean that you need some sort of engine-specific implementation, even if you're using Substrate, or does Substrate and ADBC I don't really understand this part too well, work together magically so that it actually just implements the logical plan gets executed in the same way across all these engines?
Yeah, great question. So just for some background, if you're not familiar with Substrate, it's a separate open source project started by Jacques Nadeau, who factored in the origin story of Arrow earlier. Jacques more recently started this project Substrate, which kind of has similar goals to Arrow, but is attempting to standardize compute operations instead of standardizing data format like Arrow does. Substrate is, in theory, kind of a single compute plan to rule them all. And so in theory, you'd be able to take some data frame operations or some SQL and compile it into a universal Substrate plan, which any database could understand. And you just send that through some protocol to the database and get your results back. ADBC supports both SQL and Substrate as query plans. In practice, the challenge is that there are very few systems that have actually added native support for Substrate, and those that have not done it in a fully standard way. So in practice, you still need some kind of transpilation layer or specific dialect compilation step for Substrate, the same way you do for SQL. I think there's some interesting work going on to sort of automate some of that, but it's not a solved problem now. I also say that I have not been close to the Substrate project. So if anyone has been closer to the project and wants to chime in, please do. I worked on the project a bit in the early days, but I've drifted away from it in the last couple of years.
I think your qualifier is saying in theory is painfully accurate.
Yeah. Yeah, I think there's a lot of value that folks are getting from Substrate, but not as a universal interop tool. You see a lot of use of Substrate for pretty amazing applications like within walled gardens, where you're controlling, the production and consumption of substrate plans. I know there's like some fascinating work that's going on at like Microsoft Research and other companies where that kind of stuff is done. I think there's some folks at Datadog who are also using Substrate in that way. But as a sort of magic, translation layer between different vendor components, it's got a ways to go before it'll achieve that.
So I know you're saying you say here it's not intended for OTP applications, but like again, JDBC ODBC is so bad, right? Even if you're sending a small number of tuples, I can imagine a better binary protocol would actually be better. So does ADBC support or plan to support things like begin, commit, and like other things you'd want to see in an LHP system?
Yeah, I mean, yes and no. Like in many cases, I think you're alluding to the fact that transactions, ingest, updates, things like this often are batched. They're not like single row updates, and in those cases, yes, ADBC does want to play there. I think like there's just a whole set of optimizations that you need to start thinking about if you're trying to have this be the way that like a consumer app does single row updates in a backend database. I'm sure that with enough engineering, we could make ADBC do great at that, but it's not like our first priority to make that work, in part because Arrow as a columnar format is like not going to be any more efficient than a row-based format for representing, a very, very small number of rows or a single row. And two, just because like we got to focus or we'll boil the ocean. And so yeah, transactional. I mean, I think you're raising a good point though, which is that like there's a lot of frustrations with ODBC and JDBC that go way beyond their inefficiency. They're also just really not contemporary in their developer experience and and a lot of the tooling around them. And that is an interesting like problem that in the fullness of time we might end up solving with ADBC, but it's not our focus right now.
Got it. All right, thanks.
Okay, so here's the state of ADBC today. So there's about a dozen drivers that exist for different databases, query engines, data platforms. A few of them are not yet released, but I'll talk a bit at the end about what we're planning to do at Columnar in the next few weeks. And then you can interact with those engines from about 10 or so different languages, increasing set of data frame libraries, including pandas and polars, and an increasing group of data transformation tools and BI tools, including DBT Fusion, which is the new generation of DBT based on Apache Data Fusion under the hood that uses ADBC as its underlying connector architecture, and Power BI. Power BI from Microsoft, the sort of most commonly used business intelligence tool, has begun in recent years ripping out ODBC in the places where they can and replacing it with ADBC for improved performance. And Microsoft has put an incredible amount of energy into this, both ADBC and to the broader Arrow ecosystem, implementing lots of infrastructure in C#.NET and creating drivers, collaborating with Databricks in particular and other vendors to do this. So kudos to Microsoft for being a big part of driving ADBC after they were also one of the creators of ODBC. So it's, their vote of confidence in the project is really one of the things that gives us confidence.
All right, we have a question in the chat. Will data transformation tools benefit from transactions in ADBC?
I'm not exactly sure what you mean by that context, but yeah, like we do have support for transactions in ADBC. I'm not sure like how well it's implemented across all the drivers, but like a typical analytic workflow, you don't really care about transactions. You're just running a query and getting the result. But in a transactional workflow, you have to like do several updates and then commit them at once. And yes, that kind of thing is supported by Yeah, by ADBC. When I say OLTP use cases, I'm not counting out those kind of batch updates and ingest. And I'll show later how you can use ADBC for ingest. I don't have any like transaction or commit examples in my slides, but yes, you can use ADBC for those sorts of operations, and I think they are in DBT Fusion. So I want to talk about terminology because this gets a little bit confusing with ADBC. So ADBC is an API, and this API is really a set of APIs, some of which are more abstract and some of which are concrete. So the canonical ADBC API is a header file, C header file that you can find in the ADBC repo. That is considered to be like the canonical concrete ADBC API. However, there are several other implementations, including one for Java, one for Go, which do not implement that exact same concrete API, but use it sort of abstractly to implement something that is analogous in that language. Each of the ADBC implementations also implements, or many of them implement, a higher level like set of idioms that are popular in that language. Like, for example, there is a Python implementation of ADBC, which I'll show in a moment, that implements the DB API 2.0 interface, or something that's very semantically similar to DB API because people know that and use it, familiar with it in Python. And so you should think of ADBC not as like this one single API that you need to use, but as sort of an abstract API, which is implemented in different idiomatic ways in different languages. But it also, has this core C header definition, which drives a lot of what needs to happen in the project. There is a spec in addition to the C header file, there's a specification that talks about all the different methods and so forth that you can go look at that. But it's very low level, so I will not dwell on that. I'm going to present mostly higher level Python examples later in this talk. Another important piece of terminology is driver. So I mentioned this before. An ADBC driver is a library that enables code or applications to interact with some data system through that ADBC API. An ADBC driver is also somewhat flexible. So we can implement them in different languages. Common choices are C++, C#, Go, and Rust. Typically, we choose languages that are like lower level compiled languages. ADBC drivers can be statically linked or imported directly into the same language they're implemented in. So if you wanted to, you could natively build an ADBC driver in Python. Nothing's stopping you from doing that. And you could just import it into your Python script. And as long as it spoke the Python ADBC API, you'd be good to go. But in practice, we usually start by defining lower level drivers in a compiled language, and we compile those into shared libraries or dynamic libraries. And then those can be loaded into any language using what's called a driver manager, which I'll talk about in a minute. So a shared library is this, it's a .so file for Linux, .dilib file for macOS, .dll for Windows. This is like, obviously been around for a very long time. The same architecture that ODBC used, incidentally. ODBC drivers are also shared libraries. And so a lot about ADBC is actually inspired by what worked in ODBC, and this is one of the things. So what is a driver manager? An ADBC driver manager, and I'm not a huge fan of this term, but we borrowed this from ODBC also. It's a library that acts as an intermediary between your application or code and one or more ADBC drivers. And we have ADBC driver managers for a bunch of languages: C, C++, Go, Java, Python, R, and Rust. The reason we have this is that at runtime, you might want to load a driver and use it without knowing which one you're loading in advance. Driver managers let you do that. So you link the driver manager, and then the driver manager can dynamically load drivers. And this gives you the ability to have a simple universal interface that's statically linked into your application, and then just, at runtime, choose like which specific ADBC drivers you're going to use to access which data systems. This, again, is exactly the way that ODBC works. Okay, so I mentioned there are a number of existing drivers, about a dozen or so for ADBC. Some of these are true Columnar end-to-end drivers. So this means that there's some client-server protocol that is using Arrow or some other, Columnar format that is wrapped by the ADBC driver. So the data stays in Arrow format or some other similar, Columnar format all the way through. So BigQuery, Data Fusion, Databricks, DuckDB, FlightSQL, Snowflake, those drivers are all true end-to-end columnar drivers. We've got several other drivers which use row-based client-server protocols under the hood. So those are Microsoft SQL Server, MySQL, Postgres, Redshift, and Trino. A couple of these could hypothetically use a columnar protocol under the hood, but we just haven't gotten the support from that vendor or haven't done the work to implement it. And that's an interesting kind of opportunity for us to do that. But in the meantime, we're not waiting. We've got ADBC drivers for a bunch of these systems available today. Even if they're slow, you can at least start to use them, start to migrate to ADBC. Interesting fact is that there is not a DuckDB ADBC driver. DuckDB is an ADBC driver. And this is an interesting thing. Like DuckDB itself is distributed as a shared library, a .so file, .dylib, .dll file. And if you plug that in to the driver manager, it works exactly like an ADBC driver. So there's a nice post here by Pedro Holanda at DuckDB Labs who helped to implement all this that talks about this. And I will show a few examples now that use DuckDB to demonstrate kind of what the experience is of using an ADBC driver. So step one with ADBC is import your driver manager package in Python. That's called ADBC Driver Manager. And I'm going to import this idiomatic DB API imitation library from it that allows us to use this familiar Python DB API 2.0 syntax with ADBC. We're also going to import the PyArrow library so that we can create some data to load into DuckDB. So the way that you connect to a database query engine data platform with this Python driver manager is you tell it where to find the driver. That's a path to that shared library. You tell it the name of the entry point, which is like a function defined in that C header file, which is like the main function for the driver manager to load. And then you pass it one or more arguments, which could be for a cloud data platform, things like your authentication, your credentials, which schema you're working in. For DuckDB, you just need to pass it the path to a DuckDB database file so it knows how to open up the file, which one to open up. I'm excited that we have simplified this a great deal with some new work we did recently in ADBC. We defined this new part of the ADBC spec called a driver manifest, which is very complicated internally, but what it does is it defines a specific search behavior for driver managers that looks for a TOML file, which describes where a driver is and how it works. And then that just allows us to say driver equals logical name that points to a driver, tells the driver manager what its entry point function is. Much simpler. And I'll talk a little bit more about how we were using that to build some cool stuff at Columnar at the end. So once you're connected to a database, you've got this connection object named con. We can do a bunch of stuff with it. I'll show the two most basic things you might be interested in doing. One is ingest data into that database, with ADBC. So here, what I'm doing is creating a simple 3-row, 2-column PyArrow table with what I hope are some of Andy Pavlov's favorite groups in it. And then I am loading ingesting that.
Rest in peace, double L.
Yes. Yeah, I know that's the one you're gonna lead with on this video, I hope. So this you just call the ADBC ingest function and you pass it that PyArrow table, and then the result is that DuckDB database file now has those 3 rows added to it. Even more common thing you might be interested in doing with ADBC is running a query, and this is also very simple. you call the execute method. Well, you create a cursor from the connection object, and then you call the execute method on it. This is, again, same way that you would use DB API 2.0 in Python. You pass your select statement to that execute method, and then you can fetch the result in a few different formats. There's arrow table, which is like, great arrow type of object for smaller result sets. If you want an iterator that will like lazily load the data, you can also get a record batch reader, which is like an iterator that emits, record batches. And that's what you would use, for larger data. So there's also a like a fetch, batches method that you can call. And that's the basic usage. So it's really like with ADBC, our strategy is to absorb a lot of complexity for you in order to create like a very simple developer experience. And I think in Python, this really shows. All right. So I want to jump forward now to 2030 and talk about what our vision is for where we go with ADBC from here. I think our overarching goal is to just eliminate these inefficiencies that slow data access today. I picked on ODBC and JDBC, but they are far from the only places where we see just gross inefficiency in data access. Something that surprises people is that even if you're using brand new protocols, like, for example, MCP, Model Context Protocol, this much touted, hyped protocol for connecting agents to data sources and tools and things like this. If you say wanted to send a binary columnar data set in band in MCP, guess what the only way to do it is? Base 64 encode it. That's just wild. Like, I don't know how we got there, but I think, we need ADBC to be in a lot more places. And that's one of them. There is some deliberate symmetry between what we're trying to achieve with ADBC and what the data lake table formats are trying to achieve, like Iceberg, Delta, Hoodie at the bottom of the stack. So Arrow at the top of the stack, ADBC at the top of the stack, those formats at the bottom of the stack. Each of those can kind of unify its place in the data analytics stack. We really want to bring everyone to the table with ADBC. So, like, as I mentioned, we're not relying on vendors to implement a protocol on their service side, on the server side. We can create drivers. We'd love to do this in collaboration with the open source projects, the vendors that maintain those databases, because they know their systems best. This is tricky, and frankly, it's not all carrot. There's also some stick here. Like, if you're a data platform vendor, there will be an ADBC driver for your platform. It's really up to you whether it's fast or it's slow, right? If you're a BI vendor or a data transformation vendor or an agentic analytics company, some of your competitors will implement support for ADBC and their products will be faster than yours. So, we'd really like to cooperate with folks and drive ADBC into all the places where that performance is needed. Another goal of ours with ADBC is, let me explain this. We're living right now through a Cambrian explosion of new query engines. And if you watched the sessions in this seminar series, you've seen this. DuckDB, Data Fusion, all these other engines, they're too good to ignore. And I think large enterprises that we talk to, even stodgy ones, recognize that they are leaving money on the table if they don't use things like DuckDB and Data Fusion. It's also notable that DuckDB, Data Fusion, some of these other projects can't be co-opted by a single vendor. They're set up in a way where they will fundamentally be open. But there's constant pressure in enterprise environments to like rationalize tools, consolidate vendors, like just do everything with one big mega vendor platform. And I think what we're doing with ADBC can kind of reconcile some of these competing forces. It's not really that Cambrian explosion of different engines that's the problem for enterprises. It's the fact that each of those engines brings its own set of incompatible interfaces and creates all these required security integrations and creates all these required observability hooks. That's where the problem is, and ADBC can solve a lot of that. I want to talk about a couple ways that you can help. So in a few weeks, we will be publicly announcing some tools that work with ADBC and improve the developer experience. This is open source stuff built by Columnar. I would love it if you all could sign up for our beta and try these out. If you'd like to sign up, I'll send you an email with some details, but just go to columnar.tech/beta. And we'll tell you all about DBC, which is our new driver installer, which gives you access to some of those drivers that I mentioned. If you are interested in interning or research topics, there is a lot of fascinating work that can happen in the ADBC area. I sort of mentioned some hand-wavy performance claims. We need to get our act together with benchmarking and performance engineering so we can be more confident about the numbers we're putting forward. That's a rich area of work where I'd love to bring on some folks or work with some folks who are doing kind of performance-focused research on this. And we're also building ADBC drivers. We're working to build ADBC table providers or table functions for a bunch of different systems, including Data Fusion, DuckDB. If this is interesting to you, please be in touch, and I would love to discuss this with you.
Sorry, can you explain what's a table provider again?
Yeah, so right now, if you want to load a Parquet file, there is a function that's implemented as a table generating function, a table producing function called read Parquet, right? We'd like there to be a read ADBC function for a lot of systems so that you have the same kind of easy access to an ADBC source that you'd have to a CSV file, a Parquet file, things like that. And there's been some work along these lines. This is how, for example, in pandas and polars, you can do this. But there's many other systems that you cannot yet. And so we'd love to implement that. All right, so with that, I think we have time for a little bit of Q&A.
Awesome. Thank you, Ian. I will clap on behalf of the audience. Okay, if you have a question, please feel free to unmute yourself and fire away at any time.
Hey, Ian. Really nice talk. I have two questions. The first one is all of these analytic systems, they are the same except for the parts where they are not. And one of the big parts where they are different is in things like data types. Everyone has a variant implementation now, or many of them do, and some may have JSON-B and stuff like that. And that data type type impedance mismatch also plagues the ODBC world. So are you guys taking a different approach? Of course, with Arrow, you probably have a little bit more flexibility. So would love to get your thoughts on that. And then I have a follow-up question.
Yeah, absolutely. That is something that I spend a lot of time thinking about. And I think one of the kind of key questions here. So the answer is multifaceted, right? In some cases, we'll have a database whose type system is not rich enough to feed an ADBC driver easily. An example is SQLite, right? We have a ADBC driver for SQLite. My co-founder, David Lee, worked on it. It's pretty funny what it has to do. SQLite, if you know, has I think 3 data types. And so in order to map those to the Arrow data types and convert them, we need to make guesses based on the first 100 rows. But then if we discover in row 1,000 that we were wrong about that guess, we need to go back and convert everything to a different data type. It's very complicated. A lot of that logic is baked inside the ADBC drivers. It's what makes many ADBC drivers non-trivial, is that if the data source system does not natively support Arrow, we need to convert that source, whatever it is, to Arrow. The thing is that Arrow has been around for almost 10 years, and a lot of that work has been done in some form. There's just hundreds of projects out there where people have integrated Arrow with various systems. So at least, the logic for how to do that is in many cases already implemented. It's just a matter of us finding it, bringing it into an ADBC driver and implementing it there. But you raised the second question there, which is what if the type system is too rich for Arrow, right? An example of this is this recent work which we talked about, it was brought up in the session last week, and, about variants, the work that happened to implement variants in Parquet and Iceberg. Arrow has for many, many years been attached to Parquet at the hip. So whenever Parquet does anything, we've got to jump on it and do it in Arrow. And that's exactly what we did for variant. So my co-founder Matt implemented the proposal for a variant canonical extension type in Arrow, and that was approved, and it's been implemented in a couple languages, and there's more work happening right now to implement that. I think it is very important that Arrow remains a big tent. I mean, we do want to invite everyone to the table, but a part of that is having a place for everyone at the table. So Arrow needs to evolve over time to have the richness in its type system to work with a broad set of systems. However, there's also some like release valves. So Arrow has this great multiple mechanisms of extensibility. It has first class types, then it has canonical extension types, and then it has non-canonical extension types. The latter two allow you to use underlying physical types, which in Arrow are very general and can represent almost anything, and to add your own semantics or your own meaning on top of that. That's how we've implemented many things like funky time interval and timestamp stuff, that exists in many source systems in Arrow so that it can pipe through ADBC losslessly. There's more work to be done, though. Like one thing we hear about constantly is timestamp with time zone per row. We don't have that in Arrow, and there's been a lot of serious talk about whether we need to implement it. There's some interesting other ones like that, like some of our interval types maybe don't work exactly the same way as some of the ones that popular data platforms use, and there's been a lot of push and pull about what we should do about that. But I think Arrow needs to continue evolving. Fortunately, we've shown that this old dog can do new tricks. Recently, there was not recently, it was like a couple years ago now. This huge project happened in Arrow to implement new first-class types based on academic research and industry work from CWI, from Meta, from the DuckDB folks, that showed that there's a more efficient way to represent strings, which Andy likes to call German strings. We implemented them in Arrow. It was an incredible Herculean feat, but we did it. And we're going to keep doing that because Arrow needs to be like a true high fidelity interop layer with all the systems out there that exist. That was a very long-winded answer. Sorry, Chinkesh.
No,
But
I
what
think
was your second question?
that was a great answer. I have another question that I'll see if someone else has a question. Otherwise, I will ask it.
Isaac, go for it.
Okay. So in the interest of efficiency, which you made a really good point, how far do you push compression? Of course, there's compression in Arrow Flight. And what are the current plans? And are you looking? There's obviously a ton of work happening on compression and Parquet and new formats and stuff like that. Is that part of your long-term plan to start focusing on that to make the transport be even more efficient?
Yeah, great question. So compression is a second order priority in Arrow, which may seem a little strange because it's like a first order priority in Parquet. Compression is much more important for archival storage than it is for data transfer, which is a little bit mind-blowing. But again, go back to the fact that networks have increased 10,000 times in speed since the 90s. If you're dealing with like the kind of intra data center networks that exist in many enterprise applications, you're dealing with like 100 gigabit networks. Compression in many cases slows down data transfer. However, not always, right? Sometimes you do need compression. So Arrow has the ability to define as part of its IPC format to use compression for body buffers. The arrays that actually store the data. There's a few different options there. You can also, if you're sending Arrow data through like standard HTTP, you can just compress the stream using standard HTTP compression. That turns out to work great in many cases. And some of the companies like Snowflake that have implemented Arrow in their RESTful APIs are just using standard HTTP compression because there's great support for it across many tools, and it turns out to be great. Felipe Carvalho, who's on the call, was involved in some of this work to test out these different compression options with Arrow, and it's got a nice write-up. But yeah, that is an area that is actively being looked at, but I'd say it's not a first order priority just because it turns out that in many real world applications it's not as important, nearly as important as compression is in archival storage applications.
Great. Thank you.
Other questions from the audience? Okay. So I guess my first question is like, assuming you had the best case scenario for a deployment where the client has the ADBC driver and the backend server that it's talking to has native Arrow support, so you don't have to do the SQL translation. In your experiments, you guys, what is the next bottleneck on performance implementation to solve? Like, is it the like, do you think there's more upside for more aggressive compression? I mean, we just talked about that, like, but more compression, like fast lanes and all the stuff that the Vortex guy talked about next week. Is it um, zero copy from the hardware into user space, kernel bypass or something? Like, what do you guys see as being the like next engineering challenge to solve? Again, the getting client side and the server side to all speak air natively is that's a bureaucratic issue. It can't always be solved through engineering. But what's the like in terms of like that middle piece there, what do you guys see is the biggest bottleneck?
Yeah, I think that I mean, just to address the point that you made at the end, the last mile problem is really where a lot of the value is here. I think, we don't need to do any fundamental innovation to see a lot more improvement in how fast drivers can be, because vendor support for Arrow is very spotty and very weird. I mean, for example, there's a number of systems that speak Arrow or say they speak Arrow, but if you actually look under the hood, they do very strange things. They send types in, instead of using kind of canonical arrow types for things, they will, in certain cases, like if you send a complex object, they'll convert it to JSON and send it as a string. Or
Yeah.
if you represent a timestamp a certain way, it won't come as a timestamp, it'll come as a struct of integers. And so there's like a lot of work that needs to be done just to standardize how all these things are working, to get to like full speed. But I think that what you were really looking for is the question of like, where do we need to innovate to get past the bottlenecks? And I think there's some like interesting things we could do in Arrow in the future. Like for example, Arrow right now, I mean, just give one example. Arrow right now uses bitmaps for nulls, right? It uses a null bitmap, not sentinel values. And doesn't implement support for roaring bitmaps, which is like a much more efficient way to represent bitmaps. So
Hmm.
stuff like that, I think just like continuing to incorporate research and findings and what other systems, cutting edge systems are doing, talking to the community of people who are researching file formats and engines, and just continuing to learn from them and implement things like that in Arrow. It's how we get a lot of value. It's challenging though because Arrow's stability is also sacrosanct, so we cannot like break compatibility. There's never been an Arrow 2.0. The current Arrow format version is 1.5. It remains compatible with 1.0 unless you're using some of the things that have been added more recently. So we need to think very carefully about how we implement new things to ensure we maintain compatibility. But yeah, there's some things like that I think where we can, make fundamental changes to the spec or additions to the spec that are optional that'll give you access to more performance if you need it.
You guys need is like a reverse click bench. I mean, maybe don't want to piss people off, but like a reverse click bench ranking where you like shame the vendors that one don't have native support. Like say, as you said, say look how slow you are. You don't want to be at the top, uh, and then like the compatibility matrix or something like that to say like here's all the weird things these companies are doing and like that go against what the protocol wants or expects. So. Um, Again, maybe that comes out of academia because you guys are startup, you don't piss people off, but that's a separate conversation.